Welcome again. I'm David Okot to another tutorial, another solved example on horizontal shear stresses in beams. So we'll start by reading out the question. The question is, Figure 3 shows a section of a simply supported beam which spans 5.5 meters. Determine the maximum shear stress when a UDL of 10 kN per meter is supported by the beam, and hence plot the shear stress distribution across the section. Now we have two tasks to undertake. One, to determine the maximum shear stress, and two, we have to plot the shear stress distribution. As I told you, the very first point or first thing you need to do is to, for this case, we can sketch, then use the different side. We can come here and sketch our simply supported beam is carrying a UDL. We know simply supported, we can draw it in this particular manner. So this distance here, we've been told it is 5.5 meter, and this is 10 kilonewton per meter. Now the first task I'm going to do here, I'll come and say that I know at any point the value of shear stress is given by F A y bar divided by I B. But for all the sections, for all the parts, the value of F and I are constants. They don't change irrespective of the part of the section you are dealing with. But A, Y bar, and B will change depending on whether you are talking about the flange or the web. But value of F and I does not change. Now, how do you find value of F? F is equivalent to RA, which is equivalent to RB. Remember, this is a symmetrical loading and a simply supported beam. So that will be 10 times 5.5 divided by 2. 10 times 5.5 divided by 2. So that is basically 55. On my calculator, I get 27.5 kilonewton. That will be the value of F we shall be using. Then from there, for this case, I'm not going to do what? I'm not going to compute the value of A at first, but I want to determine the position of neutral axis. So number 2, I'll move to neutral axis. How do I determine the position of neutral axis? We said neutral axis is just a horizontal line that passes through the centroid. Now, if you look at this figure, it is symmetrical about the y-axis. So which means the value of x bar is at this point, which is 150 over 2, you get 75 millimeter. But our main axis is the horizontal because this is a beam. If the horizontal axis is my main concern, then I have to compute the value of y star. Y star is the position of the neutral axis from the bottom of my T section. Now here, Y star is equivalent to, now I'll split my T section into 2. Now I can call this one area 1, and this one will be area 2. Now here I'll say my Y star is A1 Y1 plus A2 Y2 divided by capital A. Remember, capital A is the area of the entire section, which is the sum of A1 and A2. Now let's start. A1 is area of the flange, which is 150 times 30. So A1 is 150 times 30, the area of the flange, 4500 times Y1. How do you measure Y? To measure Y, you measure from the bottom most going upward, and if it is Y1, you measure to the center of area 1. Now see, for the case of Y1, the value is 200 plus a half of 30, which means it will be 215 because you measure from the bottommost to the center of the area of interest. Plus area 2, if we come here, area 2 is 200 times 20 because this is the area of web. Web is 20 millimeter thick and 200 millimeter deep. So it is 200 times 20. You get 4,000 by, what about the Y2? Y2 nitapima from where? The bottommost to the center of my web. Remember my web is 200, center yake itakuwa 200 over 2, which is 100, then all that divided by, now capital A means sum of A1 plus A2. A1 is 4500, A2 is 4000. That gives us 8500. Now, if we compute, if we punch on our calculator, give you a value 160.88 millimeter. Remember, this is from the bottom side. So you can come here on my diagram and indicate that my neutral axis. Remember, the web is what? The web is 200 millimeter, but my neutral axis is passing at 160.88 from the bottom. So which means my neutral axis is passing through the web. Now you can come here, just allow me to draw a line here and call this one the neutral axis, but let me adjust it a bit. So let me have it here. So this is my neutral axis, and we are saying that from here, from the bottommost, it is at 160.88 millimeters. So that is the position of the neutral axis. So here they wanted us to do what? To determine the value of maximum shear stress. Now, maximum shear stress occurs at the neutral axis. So I'll come and say at the neutral axis is equivalent to the maximum shear stress. But remember, it is F A y bar divided by I B. Now let's start. If we have it, now what will be the value? Now what you have to be keen enough is that at that point of neutral axis, I'm having two areas. I have that part of the web above the neutral axis and the flange. So the component AY, I have to separate them into part of web and the flange. So let's start. This AY bar will be equivalent to the sum of AY bar for flange plus the AY bar of web. Now for flange, let's start. For flange, I have the area is 150 times 30. We had it as 4500 times. What is the Y bar of flange from the neutral axis. Now, remember, I'm taking the measurement from here to the center of flange. How will I know it? I know that the total web is 200. So I'll take 200 minus 160.88. Once I get that, that is the distance from the neutral axis to where the flange start. Then I add 30 divided by 2, which is a half of flange. I'll get 54.12 millimeter. 0.12 millimeter. Sorry, I don't have to indicate millimeter. So then I add that due to web. Now let's come back here. Now, what we are computing is this one here, the whole of this area above the neutral axis. So I'm done with flange. For the case of web, the area will be, now, the vertical dimension of the web above neutral axis is 200 minus 160.88. That will give me 39.92. I multiply by 20, 39.12 times 20. That will be the area of web above the neutral axis. What about its y bar? Its y bar will be basically 200 minus 160.88. What I get, we divide it by 2 because we are measuring to the center of that area of web above the neutral axis, which is 19.56. So this component, the total AY bar will be 4500 area of flange times 54.12, which is Y bar of flange, plus 39.12 times 20 area of web part above the neutral axis times 19.56, which is the Y bar of part of web above the neutral axis. That gives us 258,843.744. Remember, this is millimeter cube because it is first moment of area. We are just taking area times that dimension. Then now I will have to go to moment of inertia. Now, moment of inertia is the I for the entire section. Now we know for moment of inertia, we can say Ixx is equivalent to Ixx1 plus Ixx2. Now here we are saying I'll compute moment of inertia for the flange plus moment of inertia for the web. Moment of inertia you take for the entire section. Now let's proceed. This is equivalent to, now moment of inertia for the flange, we know first is BD cubed, which is 30 times 150 cubed over 12, but we have the theorem of parallel axis. So I'll take that plus area 4500 into y1. Our y1 was 215 minus our y dash, which is distance to the neutral axis, 160.88, all that squared. Then I add plus that of web. That of web will be BD cubed over 12. Remember, for web BNI 20, D is 200 cubed over 12, plus, because we are using the theorem of parallel axis, plus the area is 4000 into the y. The y of web was 100. That is 100 minus 160.88 squared. Remember, this is the theorem of parallel axis. So if we work it out, that one out, So that will give us so that gives us approximately 49, 776, 715. Allow me to ignore the decimal part, or I take it 73 millimeter power 4. And then now we need the value of B. What will be the value of B? Remember the neutral axis, it passes inside the web. So the value of B at that point will be 20 millimeter and not 150 because neutral axis is inside the web. The value of B is 20 millimeter. Now we can substitute and have it as now the maximum shear stress is equivalent to F. F was 27.5. Allow me to change it to Newton so that it will be easier for plotting. We have 27,500. Now we've converted from kilonewtons to newtons times AY bar. AY bar we had it as 2588 43.744. That is F times AY bar divided by our I. We have 49, 77, 67, 15.73 times our B is 20. Now what we'll get will be in Newton per millimeter square because we converted everything to newtons. 258843.73, sorry, 744 divided by 49, 77, 67, 15.73 times 20. So this will give us 7.15, but now Newton per millimeter square. That will be the maximum value of shear stress occurring at the neutral point. But now remember, for me to be able to plot the shear stress distribution, I have to find the value of shear stress at point A, at point B, at point C, and at point D. But already at point C is the maximum, which is at the neutral axis. So it is okay. Now what I'm going to do, from the definition we said that shear stress at point A will be equivalent to 0. That is the top most. Now shear stress at point D will be equivalent to 0. That is bottom most. So the value of shear stresses at that point will be equivalent to 0. Now I'm remaining with computing the value of shear stress at point B because at point C I already have it, the maximum, which is the neutral axis. So at point B, I'm going to compute the value of shear stress twice. Why? One, because point B, the line B is through the junction between the flange and web. So I'm going to compute first shear stress due to flange and then shear stress due to web. So it will have two values on the same line. Now, and this is how we are going to proceed. So we will do it this way. Now, shear stress at point B, we can proceed. shear stress at point B is equivalent to, now it will have two values, shear stress due to flange and shear stress due to web above neutral axis. Remember, for web you must specify that above, that part above the neutral axis. Now let's start with flange. So shear stress for flange is equivalent to, the formula is still the same, F AY bar divided by AB. Now let's proceed. Now the shear force remain the same. Remember, we converted to Newton to 27,500 times. Now let's move. Area of flange, we know it is 150 times 30, 4,500. Then Y bar is a distance from neutral axis to the center of flange. We already had it as it is here, the value is here. We already had it as 54.12. We shall just substitute 54.12 divided by, now the value of I is the same. We said F and I does not change, so I'll just take that value, 49, 77, 67, 15.73 times, but now the value of B will change. For the case of flange, the value of B is 150, the horizontal dimension, and not 20. So I will use 150 here and not 20. So this will give me a value. So if I work out, this will be so this gives me 0.897 Newton per millimeter square. We say that point B I'll plot 2. Now, this is easy. For the part of web, you just take B of web, you take B of flange over B of web times the shear stress in flange. So I know that one of flange is 150, this horizontal dimension, and that one of web is 20. I multiply 0.897. So that will give me, so this times 150 divided by 20. Like the value of shear stress will be high in the web because the web is thin. And in design of steel beam, we assume the web resists the shear stresses of the shear, while the flange resists the bending moment. So the web is subjected to the highest shear. So you find that the value of shear in the web at that point is 6.727, sorry, 727 Newton per millimeter square. Now we have all the values. We can come here and plot. Let's utilize this diagram here so that we don't waste a lot of time. So what is going to happen here is I will complete these lines. So I have this line here going here, this going here, then I have through the neutral axis, then I have through the last point here. Then I'll draw now on this vertical line, it means the value of shear forces are what? 0. So if I start with the topmost point, we said the value of shear stress is 0 at the topmost and 0 at the bottommost. Now we shall move to the junction between the web and flange. First of all, we plot the value for flange 0.89. Now 0.89, I can plot it here. Now on the same, no, I'm not doing to scale, so no worries. On the same line through the junction, I plot the value of shear stress in the web, which is 6.7. Now I can move a little bit here. This is 6.7. And then from there, I move to the neutral axis where the value was. Neutral axis should be the highest value. Let's check. The value at neutral axis, you can see it is 7.15. So I plot at the neutral axis, but then it comes to 0. So if I have to complete this, I'll come now and draw. Remember, it is parabolic. I draw this way. I draw this. It comes this way. Then it comes back to 0. So you can indicate that this is 0.8. And this was 6.7, and the highest is 7.15. Remember there, Newton per millimeter squared. So this is what you are to do. Thank you so much for your attention. You can, if you like my content, you can like, subscribe, and share so that it can reach as many people as possible. See you next time on another tutorial on horizontal shear stresses.